Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, we'll continue talking about gradient descent today. Hopefully, we will finish this topic. We stopped when we were talking about when to stop gradient descent. I think we mentioned multiple ways. So gradient descent, as I mentioned last time, it is an iterative algorithm to update the values of the parameters so that we can get to the minimum of the function that we want to optimize. So we have to stop somewhere. This is an iterative algorithm. We can run it infinitely, but I don't think this will be wise. So we'll have to stop somewhere. Type when should we stop, or where we should stop? We discussed multiple things last time. Can you remind me of one?
If the gradient became close to zero.
Yes, if the gradient is close to zero, then that means that we are reaching probably a minima. Might be a local minima or maxima, or global minima, but that can be a criteria for stopping. Yes.
And the parameters no longer change.
When?
The parameter values no longer change.
Yes, when the parameter values are not changing much, then we can stop. What else? Yes.
When the performance function itself is not changing.
Yes, when the if we test the performance of the model on a div set, then we can see when the performance will plateau or will be constant. Then we can stop. And we said one more thing: when the objective function itself, the value of the objective function itself, which is the loss function in our case, is not changing much, we can also stop. So these are the four things we discussed last time. Now, how to choose the step size? I think we started to talk about that last time. One way is to keep it constant. And we mentioned last time that step size is, or choosing the step size is important, because if the step size is very small, it will take longer time to reach the minimum. If it's very large, then we might have an overshooting, which means that we might miss actually the minimum, and we might diverge even. We might not converge to a minimum. So one way is to use a constant and maybe tune it, view it as a hyperparameter that you can tune, or a better way is to start with large steps, to start the algorithm with large step sizes, and then after some time you take smaller steps. Okay, so this is dynamic, and the first idea is to make it constant, and maybe you can tune it, or you can start with large values and then make it smaller with more iterations. That's the meaning of it. Now, what's the intuition behind that? Why should we do that? Why should we start with large steps and then take smaller steps? Why do you think this might be a good idea? Faster conversions. How? Why should we start with large steps? And we usually start somewhere, right? Maybe random position. And maybe that random position might not be close to the minimum. So you want to reach the area or the region where the minimum is fastly. Okay, so you take larger steps. But then when you are a bit close to the minimum, then larger steps might make you diverge. You might really be very far suddenly from the minimum. So you have to take smaller steps. Okay, so that's the intuition. Is that clear? Now, when can you know that you are close enough to the minimum? Is there a way to know? What happens at the minimum, at one of the minimum?
If it's net zero.
Yes, when the gradient is getting smaller, right? When the gradient is small, then probably you are close to the minimum. So you might take that into consideration when you change the step size. With that, let's take a couple of examples. Let's see how gradient descent works with a couple of examples. This is the first example that you see here. This is the function x squared cosine x minus x over 10. And this is the plot of the function in specific range of x. So this is the function of one parameter. Okay, now this is not a type of the function that we would use for linear models, but this is just an example on how we can apply gradient descent on general functions, because we said that gradient descent can be used with any function. Okay, type. The question is, can we apply gradient descent here? Now, applying gradient descent here means what? Means we want to get the minimum of the function, right? Type. Can we apply gradient descent here? Why? Yes, because it's differentiable. The function is differentiable, then this is the only condition when we can apply or not gradient descent, right? If the function is differentiable, then we can apply it. Whether we will reach the global minimum or not, that's another story, but we can apply it. Type. Now, another question, is it guaranteed if we apply gradient descent to find the global minimum in this case? Why not?
We have multiple.
Yes, so we have local minimum, right? So this is a local one. This is a local one. Is that a local one or global one? Global or local? Local also, right? Where is the global? This one, right? This one. Type. It's not guaranteed to find the global minimum, right? It depends on what? Is that function convex? It's not convex. Okay. Type. Does that mean that we cannot apply gradient descent? Well, we can still apply gradient descent. Okay, we can still apply gradient descent if it's not convex. If it's convex, then we can reach the global minimum. But here, because it's not convex, we might not. Okay. Type. Is there a chance that we reach actually the global minimum here? How? Yani, tell me which value of x you think, if we started with it, then we will reach the global minimum. Raise your hand, please. Yes?
7 to
7, if x is 7, x7 is here, right? Okay, so if we started here, that means that we are here. The slope is negative or positive in this point? Negative. So should we go to the right or to the left? When the slope is negative, then when we update the parameter, we will increase it or decrease it using gradient descent. You were here last time, right? With gradient descent, what is the update rule? Do we go into to the direction of the gradient or the negative direction of the gradient? No, the opposite. The direction of the gradient is the direction of increasing the function. Okay, so if now the slope is negative, then negative times negative is positive. So we will increase the value of the parameter. Okay, so we'll go to the left or to the right. So if you remember, x will be updated by x minus eta, which is the step size, times the gradient of the function. Okay, so if the gradient is negative, that means that we'll increase x. We will go to the right. So x will increase. So probably will be here, here, or maybe here, and then we will reach the global minimum, right? Right? Do you see that? Type. If we started here, which one we will reach? Let's call them A, B, C, D. A, right? A, right? Because the slope here is positive, we'll move to the left. Okay, you see the slope? Okay, so slope will be negative, will be positive here. So we'll move to the left until we reach the of course, the step size will be a factor here. Type. Anyway, you saw you got the idea here. Let's make it more specific and take examples. Let's say that we are so this is the function that we saw in the previous slide, and now let's say that we started at 6, as I think you said, right? You said 6 or 7?
no.
6.
I said 7.
Okay, you started 7. You got the global minimum actually. Here we started with 6, So you see the slope here is positive, right? The slope of the function is positive at 6. So we will decrease the value of the parameter. So we'll go to the left. Okay? And you will see here the steps. So this is the first value. This is the second value of x here. That's the third value. And that's the fourth, fifth, and so on until we reach the minimum. But here, of course, this minimum is global or local. Local. Okay? Type. Here the step size was 0.2. This is when we start, I think here this is probably 5. Okay? And the step size is 1.5. So we increase the step size. You see here, this is different from that. The sequence here is different. Okay? So because the step size is large, we move to the left with a large step. Okay? Although maybe the slope is very similar to the slope here, but the step size is larger. So the next value from x0 is probably 1.5 instead of here we started with 6, but here it's you see the difference here. That's the update of the value of x, right? Is much larger than the update here. The update here was just this period. Are you following with me? Okay. So in this case, we will also get to the same local minima, but probably with larger steps, with larger number of steps. Yes.
The step size decreased by time because
Okay. Good question, and I will address it later today. Okay. But what you see here actually is not the step size. Yani the red lines here. What are the red lines here representing? No, that's not not my red lines. The red lines that are in the figure already.
how many times
This is not the step size. This is the change in the function value. Okay, so the function value was here, and then it became here. That's not the step size. Okay, so although the change in the function value is different here, but we are using constant step size. Okay, type. If we started somewhere else, actually we started here at 7, like what you mentioned earlier. If we started at 7, then this is the sequence that by which we will reach actually the global mean. So the minimum that we will reach, of course, depends on where we started and the step size. Okay, is that clear? Any question about this? Right. Now let's do an exercise. I want you now to take a piece of paper, each one of you, and try to apply gradient descent on this function. Now this function is x to the power 4 plus 3x to the x cubed minus 2x. I want now you to start with x0 is 1 and tell me what will be the next value of the parameter applying gradient descent on this function. If we apply gradient descent using the step size or learning rate of 0.2. What do we need to do? Yeah, so the function first is differentiable, so we can apply gradient descent, right? Type. What do we need to get first in order to apply gradient descent? The gradient, right? So here, this is the function. Let's say that this is f of x. So we need to get the gradient. Why we need to get the gradient? Because we have the rule. It says, let's do it here. X will be updated to x minus the gradient minus the learning rate times the gradient g. Okay, and what is g? G is the gradient. So let's say that g of x is the derivative of f, right? So f prime of x, which is what? Can you tell me what's the 4x cubed plus 9 plus 9 plus 9x x squared minus 2. That's calculus, right? Then we can apply the rule now. Okay, so how can we get x1? So x1 will be x0 minus the learning rate. We'll just write the equation now. Minus the learning rate times g of what? So this is g of x. Okay, so this is g of, that's the general rule. Now we are applying it to the first point. So minus the learning rate g of x0, the derivative at x0. Okay, type. Then 1 minus 0.2 times 11. So g of x0, if we substitute x by 1 here, we will get 11. Okay. So this is 1 minus 2.2, which is negative 1.2. Type. What does that mean? Any question first on that? Do you understand how we got that? Type. We started with x equals 1, which is here, right? What is f of 1? What is the value of the function when x is 1? 1 plus 3 minus 2, which is 2. So it is somewhere probably here. So that's the value of the function. Okay, when x was 1. Now x will be, the new x will be minus 1.2. Where is 1 minus 1.2? I think this is here, right? Right? What is the value of the function here? This value, right? Which is probably minus 0.6, seems like. You can, of course, substitute. So we jumped from x equals 1 to x equals minus 1.2. Type. If we continue one more step, will we go to the left or to the right? So before that, what you saw in the previous examples is something like that. You see that there is lines between the updates of the function. Okay, so that's not the step size. I think now you understand it. Okay, that's not the step size. That's how the value of the function changed. Okay, type. Where is the step size? Can we spot it here on that plot? We can't actually, because even the update is the step size times the gradient. Okay, so where is the update of the value of the parameter? Where is it? The update. The difference between the new value and the old value, right? Which is this. That's the update. That's this value, right? That's not even also the step size. That's the step size times the gradient. Okay, I think you understand now the values that we are working with. Any question about what we did? Type. Now, if we apply one more step, which direction you think x will take? The new value, left or right? Left. Let's see. What will be the slope, the new slope? It will be positive or negative? So this one was negative, right? Not negative. It was positive slope, right? It was positive slope. It was 0.2, right? You said 0.2. It was 11, sorry. 11. It was positive. So negative times positive is negative. So that's why we reduce the value of the parameter. Now the slope is positive or negative? It's also positive. Okay, so we'll go to the left. We might go here. I don't know actually. Let's compute x2. Let's see what will be the value of x2. Can someone do it with me? How can we compute x2? We will apply the same equation again, right? So can you represent x2 in terms of x1? X1.
We'll put minus again.
Yeah. It's the same, right? X1 minus the learning rate times gradient at x1. Very good. What is the gradient at x1? What x1 was minus 1.2, right? Minus 0.2 times what is the gradient at x1? 4.048. Okay, so let's assume that it is correct. Then can someone tell us what will be x2? Okay, so that means we are here, right? Yeah, so we get closer to, sorry. Okay, so we got closer here to 2. Okay, so we move to the left. Okay, next one probably will be also to the left. Type. Now let me ask you a question. First, do you have any question about this? You understand it now more? How to apply gradient descent? Any question about it? Type. You saw that with this learning rate, we managed to reach, probably we managed to reach the global minimum actually. Type. Let me ask you, what would be the value of the learning rate if we will stuck with the local minimum at the end? Okay, again, we used the step size or the learning rate to be 0.2 here, right? What could be the value of the learning rate by which we will not reach the global minimum, but will reach the local minimum instead? And you see here, when we used 0.2, starting with 1, we will reach the global minimum, right? But that's not always the case. We might have a different value for the learning rate that will not make us reach the global, but we will reach the local minimum, which is this one. What would be the learning rate in this case? Would be, you don't have to tell me exact value, but tell me whether it should be a range. It should be less than 0.2 or more than 0.2. Less than, right? Because more than 0.2 will get even more to the left, right? In that case, if the function is to infinitely going that way, then we will eventually reach the global minimum. But if it's less, probably it has to be less so that we can get somewhere in that region, right? Otherwise, we will reach the global minimum. Okay, so I will leave that to you, and I will also leave it to you to try even larger learning rate, like 1.5, and see what will happen. Okay? Any question about this? Right. The last thing that, actually two things we want to finish with, inshallah. Now you saw how we can apply gradient descent on a general function. And it is actually a general solution. Okay? It is actually an optimization solution. It's not specific to machine learning, but we use it to find good models. Now let's get back to machine learning and see how we can apply it to loss functions. Remember, the loss function has an error part and the regularizer part, right? So this is an example. If you remember, I think last week we talked about multiple ways of representing the error or the loss function and multiple ways of the regularization. So this is now a loss function for linear models using the exponential loss function and using the L2 norm regularizer. If I want now to get a good linear model, I want to optimize this, what should we do? So now this is the loss function, and I want to optimize it, which means that I want to get good values of the parameters so that I can get a good model that will minimize the loss. Okay? What is needed now? What do we need to do to run gradient descent on this function? We saw how gradient descent can be applied to any function, assuming that it's differentiable. And this one is differentiable, actually. How can we run now? What is needed? What's the first step we need to do to run gradient descent? Yes. Yes, we need to get the gradient, right? The derivative with respect to every parameter. What we did in the previous slide, the example, we had just one parameter. So we got the derivative with respect to that parameter. Now we have multiple parameters. We have multiple weights and we have a bias. So we have to get the gradient of that function with respect to the bias and with respect to the weights. Once we do that, then we can use the gradients in updating the values of the parameters. So the first one is to get the derivative with respect to b. This is in the textbook. You can, I think, go through it, just calculus. You will get, given that this is the function, we will get the derivative with respect to b. So this is the derivative eventually, and this is the derivative with respect to w. You will notice that here we are using this way of writing the derivative, but here, which is the partial derivative, because we have multiple variables, and here we are using the gradient. If you remember last time, I think, or the lecture before, we mentioned that we are using the gradient, or we are saying gradient because this is a vector actually. We are taking the derivative with respect to multiple variables, which are the weights here. So this is the gradient with respect to w, which means that it's not just one derivative, it is actually a derivative per weight. So this is actually not one, it's several. And if we have, let's say, 5 weights, so this is the derivative for 5 parameters, 5 weights. So the first one will be, here we will have W1, and here W1, the second one will be W2, W2, and so on. Okay? Type. Now let's say that we have 5 weights, and of course one bias, and we want to apply gradient descent. In every step, how many updates we will make to the parameters? And we have 6 parameters, 5 weights and a bias. Okay? So we'll have to apply the gradient update, the update rule of the gradient descent. How many times? 6 times, once per parameter. Okay, you have to understand this. We have to update every parameter separately. Okay? How we can update the parameter? Using the gradient with respect to that parameter. Okay, so we have to keep that in mind. I think we'll not have time to talk about subgradients, but I think it will be a very small topic, inshallah, next time. Do you have any question up to this point? We are very close now to finish the session of linear models. Okay, type. Where is the linear model here? Again, I'm just reminding you. It's now optimization, gradient descent, right? But where is the linear model? And if we look at this, where is the linear model? The parameters, there is a weight for each feature, right? That's why it's linear. Okay, so this is a general form of a linear model. If we use gradient descent to find the parameters, then we found a linear model. Okay, hopefully we can find, with this loss function, we can find a good global minima if possible. Then in that case we can say that we got a good linear model. But again, gradient descent can be applied to any function. Okay, any questions? Talk to you inshallah on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.